Hello everyone. My name is Nageshwar Kumar. Currently, I'm pursuing BSc Honors from IIT Guwahati, and I'm in third year. This is my internship project on the landslide prediction model using machine learning and AI techniques. The landslide is the most natural hazard that occur in mountainous and rainfall regions. It causes loss of human life, infrastructure damage, road blockage, and the traditional landslide analysis method mainly depends on manual geological surveys and expert observation. However, this approach was time-consuming, expensive, and difficult to scale for large regions. Therefore, the objective of the project was to create data-driven machine learning system that can predict landslide in the mountainous and rainfall region. The study region for our project is Dima Hassel, which is the most landslide-prone area of Assam. The main factors for landslide in this area is the terrain feature that this district possess. There is high terrain areas in the district and very intense rainfall at certain times in monsoon and pre-monsoon times. The objective was of this project was collecting and integrating geographical data sets, extracting terrain and rainfall features, handling the missing values, and training multiple machine learning models, comparing and performance, and identifying the most important factor contributing to the landslide. To solve this problem, I collected and combined multiple data sets from different geological sources, the data sets and tools. In here, I'm going to show you the data sets and tool that I have used in making the model. So, as you can see, for data set, uh, for data, I have run many scripts that collects different type of data. This script collects only DEMs, digital evolution models. This contain slope, aspect sign, aspect cost type of data for the region, for the study region. This file contains lithological data sets. This contains the land use and land cover for the Dima Haso region for over 10 years, from starting from 2015 to 2025. This is the NDVI, which is the natural vegetation, which tells us whether the area has barren land or how much vegetation does that area contain. So for that we are using this data set for 2015 to 2025. Then we have the rainfall collection file. We have run this file, but we have collected the data from Indian Meteorological Department for the rainfall. And we have collected the rainfall data set from 2015 to 2025. This is the soil type data, the soil type of the data in the region for Imahasur. And it also includes the soil moisture and bulkiness of the soil, texture of the soil, etc. things. For the most important feature for the model is landslide inventory. For this inventory, we have searched for many common files, and after searching, we got the landslide report that is uploaded on the government. We have filtered out the data only for the Assam and Dima Hasu region. For the Dima Hasu region, here is the data sets that we have used. The what we have used is we have used, as you can see, the data is collected in .tif formats. These are the highest geological data sets. And as you can see, the data set timings of dynamic world land use and land cover. We have different type of data sets. Every data set contains rainfall .tif file. All these are different EIF files. We have merged these data sets according to their CRS, the coordinate reference system, and we have aligned all these in the final output aligned form. This is the aligned .tif format for all these files. We have run the code for that alignment. We have first aligned all the, as you can see, we have first aligned all the .tif files, all TIF files, and created a multi-banded, and we have created a uh, multi-banded raster file that contains the geological features for the area in one .tif file. That .tif file is about 2.5 GBs of data, and the data is in the Here you can see the file we have created after stacking all the data bands that out the output file is 2.8 GB. Then we have done some feature after we for this process we have used Python as our main language. We have used Python Jupyter Notebook, Pandas, NumPy for our process. We have also used many geographical libraries that are present in Python, such as GeoPy, GLAD, uh, GLAD, GeoPy, whole and different libraries that we have used for geographical work. So now we come towards our model. As you can see, this is the model creation. This is the independence. As you can see, we have done the data handling part of for the model. We have total about 35 features, in which there are some features that contains many non values or zero values. We have simply removed those zero values column from our data set because that can lead to the data leakage. After this, we head towards checking more NaN values and zero values. After this, we have checked the suspicion for spike of zero values. And we can see there is a spike in landslide, and there is a spike in NDVI and mean NDVI data sets. So we have used the description to check that thing. And here is something that is faulty, and we have used the median approach to rectify that missing data in the NDVI column. Similarly, we have done this for terrain elevation also. As you can see, we have used the median statistical approach for filling the data here. We have also used this approach in aspect and terrain aspect TPIs and TWIs for filling the NaN values. After this, we have no NaN values present in our data set. Then we have done the exploratory data analysis of the clean data. Here you can see there is a highly imbalance in the class. There is more non-zero or non-landslide value present in our data set and less landslide data set present. And here are the some of the features that describes the dependency of landslide on different features. This is the feature correlation matrix, which tells us the correlation of the landslide towards the different features that are present in our data set. So as you can see, there is no direct collinearity in the features and landslide, but there is multicollinearity in the rainfall maximum and standardization because of rainfall. These all features follow the same parameters. Same goes with NDVI. After that, we have checked the random forest based importance analysis that shows us the dependency of landslide on different features, which outcome comes out to be NDVI monsoon, and moisture features. After that, we have used spatial block technique. We have not used normal train test field here because normal train test field can take the nearby latitude longitude pixel values and memorize these neighbors and predict the landslide artificially, which can lead to the data leakage and high accuracy. So for reducing the data spatial leakage and improving the model generalization, we have used spatial block technique. After that, we have used the train target split. Here we have handled the missing data, the imbalanced data that is about the 0 and 1 of the landslide. Here you can see the data is then now balanced. If you can see, there are the same 0 and 1 values. Model training. Then we have used the model training here. We are using the ensembling model technique here. Here we have all the baseline models for all the baseline model of different algorithms. Here we are using random forest classifier, XG boost classifier, light GVM classifier, and cat boost classifier. Then we are doing the individual training of these models. After that, we have done the evaluation, and the results of the evaluation are here. It shows all the picture of algorithms and their accuracy, precision, recall, and F1 score. In in landslide, the accuracy, the precision recalls matters the most because landslide can occur frequently if the rain intensity go high. So for that, light GVM performs better because it has a recall of 0.69. So here we have also produced the ROC uh, comparison for different models, and this shows the picture that light GVMB have high accuracy of prediction, which is 0.9404. After that, we have chosen the light GVME and hypertune and regularized test. For hypertuning, we are choosing this method, search space, and we have done after hypertuning. As you can see, parameter that we use for hypertuning. After hypertuning, the evaluation matrix of the light GVM are as shown here. As you can see, it has a now recall of 0.98, which is very good for the model. Then we have saved the model. After that, we are constructing an ensembling model. Here we are using four different algorithms and the modified light GVMB. After the model training, as you can see, the accuracy of here for ensembling model, there are two approaches, but we are choosing the voting approach for ensembling model. The voting ensembling model result after evaluation are shown here, which has a recall of 4.8. Why this recall is low? Because of the voting approach that we have chosen. Different models of voted for this, and the average come out to be 0.4. After that, we used the feature importance and matrix for matrix confusion. And in confusion matrix, as you can see, the stack ensembling model shows the results. There is 589 non-landslides value, and it has misled the two only. And for landslide, it has 17 non-landslide and 16 landslides value. And here is the feature importance score. It shows the important features scored according to this. That shows the highest features that are most responsible for the landslide in the area, which is NDVI, natural vegetation mean, and moisture feature mean. Then we have using again ROC curve to show the ensembling model ROC curve. As you can see, the ensembling model voting system ROC curve is 0.97, which is very good. Good as more towards one means the higher chances of good rate prediction rate. After that, we have saved the model. Then we have used spatially based model integrity analysis. As you can see, here we have chosen the mean range. These are the important features and features on which the landslide depends. Most of the time, landslide depends, and this tells us the detailed distribution of the landslide on the different features. As you can see, rain mean causes the high chances of landslide, and as we move down, it shows the low terrain aspect sign, which and vegetation persistence are the low chances. This is again a graph that shows the higher features that are responsible for the landslide and the features that are most leastly responsible for the landslide. And this plot. After that, we have saved the model. We have also uploaded the project on GitHub. So I'll be wrapping this project here. And the project was very helpful in teaching very different parts of the machine learning model. I learned different machine learning things such as feature reduction, feature reduction using ensembling model, which was very new for me. Uh, the mentor was very helpful, and there are there are some in future I would like to explore more data sets regarding the geographical data sets to improve this model. Thank you.